Hi, this is Jinge. I will introduce our paper, IVP-VAE, modeling EHR time series with the initial value problem source. Electronic health record is a digital version of a patient's medical history. It includes various types of health data, such as demographics, medications, diagnosis, laboratory results, and more. Time series can be constructed from those kind of data. However, they usually have missing values and unequal time intervals between successive measurements, as depicted in the figure, illustrating different metrics over time after ICU admission. EHR time series are in essence irregularly sampled multivariate time series. The irregularity is mainly caused by unstructured manual process, event-driven recordings, device failures, and different sampling frequencies among multiple variables. When analyzing EHR time series, a key problem is how to extract information from a sequence generated at irregular timestamps. Given a sequence, a common solution can be a recurrent neural network. However, it is unable to capture time interval information, as it assumes identical intervals between sequential observations. Additionally, in this setting, the time of the observation itself can be of crucial value and may also provide information about the underlying behavior in addition to the observed values. Some recent research has tried to propagate hidden states continuously by solving initial value problems and proposed neural ODE and neural flow. An initial value problem is an ordinary differential equation together with an initial condition. When solving IVPs, neural ODE parameterizes the derivative with a neural network. Starting from an initial point, it can calculate the states at other timestamps with a combination of a neural network and numerical integrators. Neural flow provides an efficient alternative by modeling the state transformation directly with a neural network. As they all propagate hidden states by solving IVPs, we collectively refer to them as the initial value problem source in this research. So, given a recurrent neural network, IVP source can be integrated into the recurrent operations. Originally, RNN models can only update the hidden state when an observation is collected. IVP source will continuously propagate the state between successive observations. This IVP-RNN was proven to be effective in analyzing irregularly sampled time series. Some researchers used it as a recognition module of variational autoencoder and proposed the latent ODE and its flow variant. They can model irregularly time series and also learn representation from these complex data. However, a significant drawback of these models is that they need to sequentially solve a large number of initial value problems. For example, if we take a neural ODE as the IVP source, L is the sequence length, S is the number of evaluations. The total computation steps are S multiplied L, which can make the model quite slow for processing time series. Based on the previous research, our contribution is we propose a novel continuous time model, capturing sequential patterns of EHR time series by purely solving multiple IVPs in parallel. We provide a more efficient generative modeling technique, achieving parameter sharing between the encoder and the decoder of the VAE architecture by utilizing the invertibility of IVP source. The model achieves higher efficiency compared to its predecessors and comparable performance to state-of-the-art models. The model achieves significant improvement over all baselines in settings where the training data is limited. The key idea that our model builds upon is that time series values are discrete observations of an unknown continuous process. Each sample corresponds to a continuous process, of which we obtain an indirect observation at each available timestamp. In this sense, our proposed model IVP-VAE is essentially a generative model for these continuous processes. The model is trained as a VAE. In the encoder part, the embedding module extracts information from the multiple variables and map observations into the latent space. Afterwards, the state evolves backward in time. Here, the initial condition is Zi, and the IVP store is used to calculate the state at T0, and then sampling the posterior of Z in the VAE. In the decoder part, the latent state evolves forward in time to obtain the state at different timestamps using the same IVP store. That means we take Z0 as the initial condition and go opposite along the timeline to recover the temporal trajectory. Finally, all latent states are mapped back to observations by the reconstruction module. So for the states involving, compared to latent ODE, our model eliminates the recurrent units and solves multiple initial value problems in parallel. Another contribution is that we fuse the encoder and decoder with one IVP source. This can be achieved because IVP sources are invertible. More specifically, first, for the case of ODEs, giving an ordinary differential equation as an example, we can obtain its slope field, and the derivative is determined everywhere, but the delta t can be negative or positive, which will determine the moving direction along the slope. As shown in the figure, starting from different initial conditions, we can obtain the values at other timestamps using the Euler method. Zi and Z0 are on the same integral curve. One can calculate forward and backward using the same IVP source. And then as for the case of flows, mathematically a flow is defined as a group action on a given site, and it follows certain properties. These properties naturally guarantee invertibility. If Tj equals negative Ti, then the combination of the two operations can describe the process of encoder and decoder. Neural flows can be trained within the VAE framework forward and backward in time to obtain this behavior. To train the model, we follow the VAE training approach and minimize the evidence lower bound. We also augment the model with supervised training objectives. We tested our model on two tasks, time series classification and forecasting. We evaluated the model on 3 public EHR datasets with different characteristics such as sample size, variables, missing rates, etc. We compare our model against the several baselines of multivariate irregular time series. To have a clear view of the improvement in terms of performance and efficiency, we make a detailed comparison of our design and the latent-based models on the 3 datasets. Corresponding to latent ODE and latent flow, we evaluate IVP-VAE with 2 types of IVP source. From the result, we can see that our model can achieve better classification and forecasting performance. Significant speed advantage, faster convergence, as well as a smaller model size. Here is the comparison against the state-of-art baselines. We can see that our model achieves competitive performance across all datasets and tasks. To further demonstrate the capability of the proposed model, we examine the performance under low sample size condition. This scenario is analogous to a rare disease setting and in the field of EHR prediction, where data can only be obtained for small cohorts of patients. The figure compares the performance of 4 typical methods on small datasets, where we collected only a limited number of samples for model training and validation. As we can see, for both forecast and classification tasks, the IVP-VAE-based model consistently outperforms other baselines across a different number of samples. To summarize, we provide a lighter and more efficient continuous time generative model. The modeling and the representation learning of irregularly sampled EHR time series are achieved by solving IVPs in parallel. The proposed model is much faster than its latent-based predecessors, performs comparably or better than other baselines on classification and forecasting tasks, and achieves significant improvement in scenarios where the training data is limited. Thank you.